Okay, hopefully you can see my slides now and you can hear me. So thanks for inviting me to speak today. I want to talk about the technical evaluation of SMETER technologies, or the TEST project, and this was funded by the UK's Department for Business, Energy and Industrial Strategy. So obviously this was a big project, and a huge thanks to the project team, all my colleagues at Loughborough University, Gav, Lee and all the brilliant team at Alton Housing, Chris Gorse and all the Leeds Beckett team, and Cliff Elwell and all the UCL team. I'm sure you'll recognise there's some friends of Annex 71 who are all part of this, and hats off to all of them for the work that they put in. Also want to acknowledge the support that we had from KU Leuven in this project. Thank you, staff and others. And also just to acknowledge that really Annex 71, I think, has been fundamental to not only our thinking as we work on this project, but also as the inspiration to BEIS when they set the project up as well. So the aim of the TEST project was to evaluate the performance of these SMETER technologies, and these were being developed under separate funding. SMETER is a smart meter enabled thermal efficiency rating, not my acronym, and SMETERs calculate the heat transfer coefficient of homes using smart meter data. The field trial that I'm going to talk to you about today had 8 SMETER technologies from 8 participating organisations. 2 of them only used gas and electricity smart meter data. They didn't have any sensors in the house. The other 6, they had some sensors in the home, and some of them it even included things such as that they were integrated in a heating controller. We had 6 stages in the project across 2 different phases. Really, phase 1 was kind of for 2 reasons. First of all, we needed to set up the field trial, and that was going to take time. But secondly, it was also an opportunity for the participants to develop their algorithms. And we created some simulated data using Energy Plus for them to, to have a go at. I'm not sure on the value of simulated data. I think there's some question marks over that, but at least it was an opportunity for us to sanity check that these algorithms could come up with something sensible. And we also observed the SMETERs being installed in our test houses here at Loughborough. So that led to a stage gate, and everyone got through the stage gate very happily. And we started on this field trial, and this is the main bit that I'm going to talk about today. So in the field trial, we had 30 homes provided by Alton Housing. And you can see a little bit about them there. They were kind of varied, but mainly semi-detached or end terrace, and relatively small houses, perhaps 38 to 83 square meters. Every single one of those homes was surveyed in detail. A co-heating test and blower door test were carried out to measure the HTC, and Leeds Beckett also looked at QUB and pulse alternatives to co-heating and blower door. And then we installed secondary gas and electricity meters, temperature relative humidity sensors, and that provided us with monitored data from all of the homes. And then each SMETER was allocated to 10 homes. So 8 SMETERs, each was allocated to 10 homes. A SMETER product installed where needed. We had 2 or 3 products in each of the houses. And then and only then did a household move into the home, and we started the trial. So after the first partial winter, each of the 8 participating organisations reported the HTC of each of the homes along with a 95% confidence interval, and we compared that with the measured HTC from our co-heating and blower door. And it's important to say this was a blind trial, so the participating organisations didn't know the measured HTC values. And the results I'm going to give you here are from an intermediate stage. They're not the final results. But the final results are not going to be a great deal different to what you see here. So this is an example of the results for one of the homes. So you can see that the measured HTC was about 150 watts per Kelvin-ish, with a 95% confidence interval from 133 to 178. And then each of the SMETERs gave their own calculation of the HTC, and each one had its own confidence interval. So that's an example of what the results looked like. In order to evaluate the SMETER accuracy, we did this 3 ways. Firstly, we compared the SMETER calculated HTC with our measured HTC looking to see if those confidence intervals overlapped. Secondly, we looked at the difference for each home. What was the difference between the SMETER result and the measured HTC? And we used this to calculate some statistics, which some metrics to describe the accuracy, and I'll explain them a little bit more later. And then finally, we compared how accurate were the SMETERs compared with how accurate is what we called expert RD-SAP. So RD-SAP is the UK's national calculation methodology under the EPD for energy performance certificates, and in there's a calculation of the HTC. We call it expert RD-SAP because this was done by a very expert team of surveyors and users of the RD-SAP software. So we don't think user error came into this. It was more looking at the underlying model or methodology. So these are the three ways, and I'll just go through the results of each in turn. So first of all, for comparison of the calculated HTC, in this fictitious example, you can see the co-heating test has an interval here. SMETER 1 and 2, well, their confidence intervals overlap with the co-heating test, so we would say they were successful, and SMETER 3 just falls short, so we would say that was unsuccessful. So looking at some real results next, you can see here that these are the 8 SMETERs, and the number of results with overlapping confidence intervals ranged from one of the SMETERs was correct in every case, and they all did pretty well. The lowest was 77%. So it was clear that this was possible, but obviously calculating confidence intervals, estimating confidence intervals is a little bit tricky. You can see that the average confidence intervals for the different techniques ranged from plus or minus 13% up to plus or minus 45%. So there's quite a range, and it's a really challenging thing to try and do. And obviously, in this trial, all of the participating organisations wanted to show that their confidence intervals were as low as possible. But then the risk is if you have a very low confidence interval that you have fewer with overlapping confidence interval. And this was kind of deliberately built into the evaluation to kind of help and advance our thinking of how we might calculate uncertainty in these cases. But confidence intervals aren't everything, and so we did this analysis of the differences as well. So these box whiskers, there's one for each SMETER, and you can see for the first SMETER, these are the results from the 30 homes and the difference between the measured HTC. And this is the bar here in the middle shows the median results, the cross is the average result, and here you have the range of results. So this first SMETER here has an average that's it's kind of biased. On average, it's giving less than the measured HTC, and the range is quite large. Whereas for this particular SMETER, the average is pretty much zero, so there's much less bias and there's much less spread. So we might say this one is more accurate than that one. And these are the metrics that I mentioned earlier. The first one was the average difference, which is we used the normalized mean bias error. It gives you a measure of trueness or systematic agreement, and ideally you would be zero or as close to zero, positive or negative as possible. And then the second one is the coefficient of variation of root mean square error, and here it's a comparative measure of the precision for these 30 homes, and the lower the value you get here, the better. So looking at the results for the SMETERs here, you can say that the normalized mean bias error ranged from about 0 all the way up to minus 12% was the largest bias, and the coefficient of variation of root mean square error ranged from about 13% up to about 33% for these cases. So then the third thing, so now we had these metrics to show what the accuracy was. We could compare it with what expert RD-SAP predicted would be the HTC of the homes, and you can see perhaps surprisingly the bias was relatively small for the expert RD-SAP, and the range was not as big as perhaps we'd expected, but these were quite simple houses, I assume. But you can also see that if we take the normalised mean bias error of -3% and the coefficient of root mean square error of 18% for expert RD SAP, then 3 of the SMETER technologies in this evaluation gave results that were better based on these 2 metrics than the expert RD SAP. So I think this is really encouraging. We've got some results that are going to follow soon. First of all, we ran the field trial for another winter, and so we've got some of the participating organisations have updated their results because there was more data available. It was a short winter period, the first one, and we're going to have a look at those, and we'll be reporting those soon. And then we also looked at what do you get if you have a commercial EPC assessor do those assessments. What do we see? Do we start to introduce some human error perhaps in those EPC RDSAP HTCs? There were a couple of limitations. All the homes were EPC band C or D. They all had gas boilers. There were no flats or mid terraces to complicate things with the party wall heat losses. So in some ways the field trial was limited, but it was definitely a good starting point for this evaluation. So very quickly to summarise that, before I say a few other things, there were 8 different SMETER technologies, and all of them could calculate the HTC of the homes in the field trial. They had uncertainty that ranged from the best to the worst, and we developed these, or we used these measures of trueness and precision that were really useful in this case. The best performing SMETERs were better than the expert RDSAT, which is really encouraging. And I think it's fair to say that further work is now required to extend the findings to more types of homes and different types of heating systems. This has resulted in an open access data set, and I'm sure if these slides aren't being shared, then we can definitely share this out to everybody, but there's a DOI for it here. The data set currently has data for 15 dwellings, and the measured HTC has been omitted from that data set, but we're going to be soon adding the data for the other 15 homes, so all 30 homes will be on there, and BEIS have given permission that we can release the measured HTC for 15 of those homes. So this is a great opportunity for more people to develop these algorithms, I think. I was reflecting on what I think are some interesting topics for future research, and I think there's a few things that I'm interested in anyway. Fundamentally, we might agree on a definition of HTC and what to do about some of the complications around it. We should explore perhaps the validity of, for those of you who get my annotation, the sigma AU plus a third NV, and this fact that U values are assumed to be independent of air temperature. Perhaps in poorly insulated homes that assumption doesn't hold so well. And then thinking about how does the HTC change through a year as the ground temperature changes, or maybe on smaller timescales as wind speed changes. Obviously we're looking HTC as an average value, and that's fine, but we need to understand some of its variation. We might look at further application of these in situ methods. So can we look at more dwelling types, bigger homes, new homes, flats? Can we look at homes with different energy systems that might make that measurement of heat inputs more important, particularly if some of that energy is being used outside of the dwelling, perhaps in the garden or for EVs? What is the repeatability of the measurements? How can we improve the estimation and communication of uncertainty? This is really important. All measurement is uncertain. Let's not get hung up on the fact it's uncertain, but how do we better communicate that? How do we better estimate it? And how do we continue to develop the algorithms to be even more accurate? And then if we're looking at benchmarking these methods, then the co-heating test is I believe the most effective way to do that. And we can continue to develop the co-heating test. We already in this project started looking at innovation on how we collect the data and analyze it. And for sure, I think we need a better way of measuring ventilation infiltration. This kind of Q50/20 just doesn't work, at least in my experience. And a final thought, consumer engagement. How do we better communicate thermal performance? perhaps something around education, but perhaps also we need to think about these metrics. I can imagine a day when people are in the pub talking about the HTC of their home or some other metric in the same way as they might about the miles per gallon or kilometres per litre in their car. So my personal reflection on the Annex 71 journey, about a decade ago, I managed to persuade this young man, who some of you might recognise, that it was HTC was a really interesting thing that he might look at trying to measure in his PhD. In 2015, I was lucky enough to meet staff, and that led to me getting involved in Annex 71. In 2017, I had the privilege of inviting everyone to Loughborough, and that will always stick in my mind as a huge memory. In 2018, the UK government announced this invitation to tender for this technical assessment contractor, which later became the test project that has dominated my life through 2019 and 2021. So I guess the question's what's next? My favourite quote from Lord Kelvin: when you can measure what you are speaking about and express it in numbers, you know something about it, but when you cannot measure it, when you cannot express it in numbers, your knowledge is of a meagre and unsatisfactory kind. And I think, if you know, I drove to work in my car this morning, I was dazzled by all the information it told me about speed, miles per gallon, miles per hour, average speed, fuel. And yet still, if I can find the meter in my home, it tells me something as useless as the cubic feet of gas that have gone through this meter since it was installed, goodness knows how many years ago. So I would argue that we need a revolution, and we should be routinely measuring the thermal performance of homes. Why would such a large product have no quality assurance? So I offer my sincere thanks to you staff for bringing us all together in this annex. It's been an incredible experience for me, and also to all the revolutionaries of Annex 71. It's been a huge privilege to meet you all and work with you. I hope we can all keep working together on this. I hope we can keep talking. I hope we can keep sharing what we find. I think this has been just the most brilliant opportunity, and please, anybody, do feel free to get in touch with me at any time to discuss this further. Thank you very much.